Before we learn to solve differential equations, we want to be able to classify different types of differential equations. In other words, given a specific differential equation, we want to be able to recognize what kind of differential equation we're even looking at. Now, in general, differential equations can be broken up into two categories: partial differential equations and ordinary differential equations. Now, remember that a partial derivative, if we have something like a multivariable function, f of xy, in other words, a function f defined in terms of two variables, x and y, so this is a multivariable or multivariate function. If we want to take the derivative of a function like this, we can't just take one derivative because f is defined in terms of two variables. So would we take the derivative with respect to x, or would we take the derivative with respect to y? The answer is that we can't accomplish this in one derivative. We have to break up the derivatives into two partial derivatives, one partial derivative with respect to the variable x, and one partial derivative with respect to the variable y. So the derivative of a multivariable function is actually given in two parts. We have the partial derivative of f with respect to the variable x, and then we have the partial derivative of the function f with respect to the variable y. This little symbol here is this partial symbol. It indicates a partial derivative. And when we see partial derivative notation like this, it means the partial derivative of this function here in the numerator, you can think of it as, so the partial derivative of the function f, and then the variable we have in the denominator is the variable we're differentiating. So the partial derivative of the function f with respect to the variable x, as opposed to over here with respect to the variable y. When we have an equation that includes partial derivatives like these, then of course we call it a partial differential equation, or a PDE, partial differential equation. Partial differential equations, so equations involving these partial derivatives, are not going to be the primary focus of this course. The primary focus will be on ordinary differential equations. And these are equations that include ordinary derivatives, which are derivatives of a function defined in a single variable. So for instance, if we have some function y of x, this is the function y defined in terms of one variable, x, as opposed to this function f, which was defined in two variables, x and y. Because this function is defined in terms of just one variable, when we take its derivative, we don't have to take partial derivatives with respect to each variable in the equation. There's only one variable, and so we only need one derivative in order to differentiate this function y of x. Our derivative can be given in several notations. So all of these mean the same thing, but they're just written different ways. So we can write this as y prime of x, and these will look familiar from calculus, but we can write this as y prime of x. Sometimes we just write it as y prime, or we can write the derivative in Leibniz notation as dy dx, which is just another way to indicate the derivative of y with respect to the single variable x. All of these, y prime of x, y prime, and dy dx, all represent the derivative of the function y of x. So any equation that includes a derivative written in any of these notations would be an ordinary differential equation. And we would call that an ODE, an ordinary differential equation. So an example might be dy dx, the Leibniz notation for the derivative. And if we wrote something like minus sine x cosine x equal to 2x, this is an equation, and it includes inside of it a derivative. Because the equation includes an ordinary derivative, it's an ordinary differential equation. Now, when it comes to classifying ordinary differential equations, we're interested primarily in three things: their order, their linearity, and their homogeneity, whether they're homogeneous or non-homogeneous. So we want to talk about the definitions of those three things, and then look at some examples of ordinary differential equations and define their order, linearity, and homogeneity. So these are all examples of ordinary differential equations because you can see that they all include ordinary derivatives. In this case, we've written all the derivatives as y prime, y double prime, y triple prime, but you can see that we have no partial derivatives included here. So these are all ordinary differential equations. The order of a differential equation is given by the highest degree derivative that's included in the equation. So for example, this first equation here, we have y prime, and y triple prime. So the order of this equation is 3. In other words, it's a third order differential equation because the highest degree derivative is a third degree derivative. Compare that to the second equation here where we have y prime, and y double prime. The highest degree derivative is the second derivative, and therefore the order of this differential equation is 2. It's a second order differential equation. Here, the only derivative that's included is y prime. That's the first derivative, so the order is 1. In this equation here, we have the first derivative and the third derivative, so the order is 3. Here, the order is 2. We have the second derivative, y prime here, that's the highest degree derivative. And in the final equation here, we have just y and y prime. We have a first derivative, that's the highest degree derivative, and so the order is 1. So that is the order of the differential equation. The linearity of a differential equation is just whether or not we can consider the equation to be a linear equation or a nonlinear equation. A differential equation is going to be linear when the only values of y that are included in the equation are y itself and its derivatives. We can't have any other kind of function involving y. So for example, in this first equation here, we see y in 3 places. We have cosine of y, we have 2y prime, and we have 8y triple prime. These first 2 terms are fine. They just include derivatives of y prime and y triple prime, and those are multiplied by constants. But here, we have a different kind of function in y. We have cosine of y. And because we have this other kind of function that involves y, this is a nonlinear equation. So we'll say nonlinear. Another way to put this more formally would be to say that all the coefficients on these derivatives are functions in terms of x only. So the coefficient here on y triple prime is just 8. We can call that a function in x. In other words, it's not a function in y. 2 is just a constant function. We can say that's a function in terms of x. But this cosine of y here is not y with a coefficient function in terms of x only. It's a function of y, cosine of y. So that's why the cosine of y term makes this equation nonlinear. So all the coefficients on y and its derivatives have to be functions in terms of x. This function over here on the right-hand side has to be in terms of x only as well. If it's some function of x mixed with y or multiplied by y, then the equation would be nonlinear. And again, we can't have any other types of functions in terms of y. So no cosine of y, no y squared, no e to the y, no natural log of y. Those make the equation nonlinear. So let's do some other examples so we get the idea. Here we have y prime and a coefficient function in terms of x. Here we have y double prime and a coefficient function in terms of x. These are just constant coefficients. There's no problem there. And over here on the right-hand side, if we go ahead and subtract xy from both sides, then we can rewrite this. Let's cancel out this part here. And we'll rewrite this as minus xy equals 0. So now we have 2y double prime plus 5y prime minus xy equals 0. On the left-hand side here, we have y prime, and y double prime. And their coefficient functions are all functions in terms of x only. And over here on the right-hand side, we have a function in terms of x only. And there are no other functions of y, like cosine of y or y squared, anything like that. So we meet the criteria here. This is a linear equation. If we look at this third example, we can see right away we have a problem here with this e to the x plus y term. This is a function in y, not just y multiplied by some coefficient function in terms of x only. So this term is an issue that makes the equation nonlinear. Otherwise, we wouldn't have a problem with the other 2 terms. E to the 2x on the right-hand side is a function in x only. That's fine. And over here on the left-hand side, the e to the xy prime, we have a coefficient function in terms of x only multiplied by this first derivative of y. no issue there in terms of making the equation linear. It's this middle term here where we have some other kind of function in terms of y that makes the equation nonlinear. This equation here, just like before, if we subtract y times cosine of x from both sides, we'll rewrite this as minus y cosine x equals 0. And now over here on the left, we have y triple prime plus 5y prime minus y cosine x. We just have y prime, and y triple prime, so y and its derivatives, and the coefficients on those terms are all functions in terms of x. The function in front of the third derivative is 1, a constant function. The coefficient on y prime is 5, a constant function, a constant coefficient. And the coefficient on y is cosine of x, a function in terms of x only. So we're good there. There's no other kind of function in terms of y. And the right-hand side is 0, a function in terms of x only. So we can call this a linear equation. Same with this equation here. We just have y and its derivatives on the left-hand side with coefficients on those terms that are in terms of x only. And we have a function on the right that's in terms of x only. So this is linear. And then this last equation here works as well. On the left-hand side, we have y and its derivatives, and the coefficients on those terms are functions in terms of just x. And on the right-hand side, we have a function in terms of x. This is a linear equation as well. And then the last thing we want to look at is the homogeneity of an equation. And this one's really easy because it's just about whether or not this right-hand side, when we've written the equation in standard form like this, whether or not the right-hand side is equal to 0. And this homogeneity question only applies to linear equations. In other words, we only bother classifying linear equations as homogeneous or non-homogeneous. So we can see right away that the second equation here and the fourth equation here are homogeneous because their right-hand sides are equal to 0. So we'll call this homogeneous, and the fourth equation as well. But the last two equations, where we have sine of x on the right side and x squared minus x plus 1 on the right side, because those values are non-zero, we call them non-homogeneous equations. So we'll say that these are non-homogeneous. Now you may be wondering why we can't call these last two equations homogeneous if we just subtract the terms on the right-hand side from both sides to move them over to the left. In other words, this equation here, if we were to rewrite it as y double prime minus 3y minus sine of x equals 0, why can't we call this a homogeneous equation? Well, it's because of the form of the equation. We want to put this in standard form, and that means that on the left-hand side, we only include those terms where we have y and the derivatives of y. So that's our y double prime minus 3y. When we have some function in our equation in terms of x only, we keep that on the right-hand side. That's why we have sine of x that doesn't include y over here on the right-hand side of the equation by itself. The left-hand side should only include the terms involving y and the derivatives of y. So in this form with sine of x on the right, now the right-hand side is non-zero, and so we call that non-homogeneous. Same thing with the last equation here. We've written it in a form such that we only have y and its derivatives on the left, and then anything that doesn't include y, just these x terms over here on the right. And because the right-hand side in this form is non-zero, we call it non-homogeneous. Now going forward, when we're talking about ordinary differential equations, we describe them by their properties, their order, their linearity, and their homogeneity. So we would call this first order equation a third order nonlinear equation. We would call the second equation here a second order linear homogeneous equation, or a linear second order homogeneous equation. Depending on the context, we won't always use the full designation to describe the equation. In other words, maybe whatever we're doing with it, we're not necessarily interested in the order of the equation, or it's just obvious and we need to point it out. So maybe we would just describe this equation as a linear homogeneous equation, or just as a homogeneous equation, because that's the point that we're focusing on. But if we want to be really thorough, or we need to be very clear about what we're talking about, we could call this a second order linear homogeneous equation, or a linear second order homogeneous equation. This would be a first order nonlinear equation, a third order linear homogeneous equation, and then these last two, a second order linear non-homogeneous equation or a linear second order non-homogeneous equation. And this last equation would just be first order of the same thing. So hopefully that gives you a better idea of the kinds of differential equations we'll be looking at. And going forward, you'll know what we're talking about when we say something like a third order linear homogeneous equation. The first kind of differential equation that we want to look at is a first order linear differential equation, which is a differential equation given in this form. What we notice right away is that it's a linear equation because in terms of y, we only have y and its derivatives included in the equation. We don't have any other functions in y like sine of y or y squared, anything like that. We just have y here. And then we have the derivative of y. This is written in Leibniz notation, but we could also write this as y prime. So we just have y and y prime, so it's a linear equation. We also know that it's a first order equation because the only derivative that's included in the equation is a first order derivative. dy dx is a first order derivative or a first derivative. So this is a first order linear differential equation. This is the first kind of equation that we want to learn how to solve. The steps that we're going to use to solve this equation are these 6 steps here, and we'll go through each one of these in detail. The first one being that we want to match the form of our equation to this standard form of a first order linear differential equation. Basically, all that means is that we might have a first order linear equation, but it may not be written exactly this way. For instance, maybe the p of x times y term is subtracted over here on the right side of the equation instead of added over here. Or maybe the derivative term is subtracted over here on the right instead of on the left. In other words, the equation that we have may not look like this immediately. We might have to do some manipulation to get it in this exact perfect standard form. And that's what we mean by matching the form or matching the format of this differential equation. We want to take the equation we have, and if we can put it into this exact form where we have the derivative of y by itself here, some function p of x, multiplied by y itself set equal to some other function of x, then we have this exact form here, and it's a linear first order differential equation. One other thing we want to say before we work through the rest of these steps is that once we have the equation in this form, we have 2 possibilities here for q. We can have a q of x function that is equal to 0, or we can have a q of x function that is non-zero or not equal to 0. When the q of x function is equal to 0, we call the equation homogeneous because this is a differential equation set equal to 0, so it's a homogeneous equation. When the q of x function is not equal to 0, we call the equation non-homogeneous. Homogeneous linear first order equations are also called separable differential equations, and we can solve those using another method, so we'll save that for a later lesson. The equations we want to focus on right now are the non-homogeneous equations where q of x is not equal to 0. So we have some function in x over here that's not equal to 0. In that case, we're dealing with a linear equation that's not separable, so we won't be able to solve it as a separable equation. We'll have to use these steps to solve it as a linear equation. So to illustrate how we'll use these steps to solve the first order linear non-homogeneous equation, let's work through an example. Let's say that we've been given the equation. We'll say dy dx plus 2y is equal to 4e to the negative 2x. Now we can see right away that this is a first order linear differential equation and that it's non-homogeneous. It matches exactly the form that we have over here. We have the derivative dy dx by itself without any kind of coefficient. It's not multiplied by anything else. We have the 2y term here, which matches this p of x y term. The p of x function is 2. Even though we don't have an x variable that's visible, that's still a function in x. It's just a constant function that's multiplied by y. And then we have the q of x function over here on the right. This is non-zero. It's not equal to 0, so it's the non-homogeneous kind of linear first-order differential equation, and we'll therefore use these steps to solve it. So this equation is already in this perfect standard form, so that's step 1 taken care of. For step 2, we just need to identify p of x and q of x. And all we have to do there is match up our standard form over here to the equation we've been given. So we see here p of x, and then we have q of x equal to 4e to the negative 2x. So we match those values. And then once we've done step 2, the important part is p of x, because we're going to use that for step 3, which is to find what we call the integrating factor. And we'll look more at this integrating factor later. For now, we just want to talk about how to calculate it. So the integrating factor then, we say is I of x. That's going to be equal to e to the integral of the function p of x. In our case, that's 2. So 2 dx. And now we just need to evaluate this right-hand side. The integral of 2 is 2x. So this is just equal to e to the 2x. This function then is what we call our integrating factor. Now again, we haven't explained yet why we're calculating this random e to the integral of p of x value. We'll talk more about that later and work through a proof of why this value is going to be so helpful to us. For now, we'll just calculate it, finish with the rest of these solution steps, and then we'll talk more about this later. So once we have this integrating factor, our next step is to multiply through the differential equation by the integrating factor. In other words, we take this differential equation here and we multiply through both sides of the equation by the integrating factor e to the 2x. So we would go ahead and say here, let's go ahead and change this to y prime. We'll just write it as y prime instead of dy dx. So we'll say y prime multiplied by e to the 2x plus, here we'll say 2e to the 2x, so 2e to the 2x y, and then we'll set that equal to, over here on the right-hand side, 4e to the negative 2x multiplied by e to the positive 2x. Remember that when we multiply exponential terms together, we add the exponents. Well, negative 2x plus a positive 2x is 0. So we get 4e to the 0. E to the 0 is 1. And so we get 4 times 1, or just 4. Now, once we have this equation here, we can actually rewrite the left-hand side of the equation. What we notice here is that the left-hand side of the equation is actually just an expanded form of the derivative of a product. In other words, think back to the product rule for derivatives that we learned in Calculus 1. Remember from Calculus 1 that when we said we wanted to take the derivative of the product of two functions, so we'll say f of x times g of x, we have the product of two functions, that was equal to the derivative of the first function, so f prime of x, multiplied by the second function, g of x, and then add to that the first function, f of x, multiplied by the derivative of the second function, so g prime of x. Well, what we notice here is that if we call y f of x, so if we say that y here is f of x, then y prime over here is f prime of x. And then if we say that e to the 2x is g of x, then the derivative of e to the 2x is 2e to the 2x. And we notice here that we have g prime of x. When we add these together, as they are added together, what we see is that this is the expanded form of the product rule. So we can actually reverse this or undo it and say that this expanded form is equal to the derivative of the product of f of x and g of x. So this left-hand side here, when we reverse the product rule, becomes the derivative d dx of f of x, which we said was y, so y, multiplied by g of x, which we said was e to the 2x. So y e to the 2x, and then we keep the equals 4. What we notice here is that the left-hand side is the derivative d dx of y multiplied by the integrating factor. E to the 2x here is the integrating factor I of x. And notice here that that's step 5, the derivative d dx of y multiplied by the integrating factor. And that is why the integrating factor is so useful to us. When we follow this method, we're always going to end up with a left-hand side that is equal to this expanded product rule, and we'll be able to reverse the product rule to rewrite this left-hand side as the derivative of y multiplied by the integrating factor. So in fact, as we get more comfortable with this process, as soon as we identify the integrating factor, as soon as we find e to the 2x, we can skip straight to step 5 and write an equation for the derivative of y times the integrating factor set equal to this right-hand side here. Once we have this equation, then our last step is to integrate both sides and solve for y to find the general solution to this differential equation. So if we integrate both sides, we'll rewrite this as the integral of d dx y e to the 2x, and because we're integrating, we'll say dx here, equal to the integral of 4 dx. When we integrate a derivative, remember integration is the opposite operation of differentiation. So these two things here cancel each other out. The integral cancels the derivative and vice versa. Those two things cancel each other out. Those operations undo each other. So the left side becomes just ye to the 2x, or y times the integrating factor. And the right side, we integrate. The integral of 4 is 4x, so we get 4x, and then we add c to account for an unknown constant of integration. Now we can go ahead and solve for y. In this case, all we have to do is divide by e to the 2x. So we get y is equal to 4x plus c divided by e to the 2x. And this is the general solution to our first order linear differential equation, meaning that this is the value we found for y here. If we plug this value in for y, it's the value of y that makes this differential equation true. It's the value of y that makes this equation true, that solves this equation. This is the general solution to the first order linear differential equation. So that, in general, is the set of steps that we follow to solve a first order linear differential equation. And we talked about it a little bit already, but let's circle back to this idea of the integrating factor, because it's by far the most interesting and critical part of this solution process. So just to reinforce why this integrating factor actually works, let's go ahead and pop the general solution up here. So the general solution we found was y equal to 4x plus c divided by e to the 2x, and then we'll clear some room to investigate this a little more. So in general, the reason that this works, let's kind of go through a little proof of that integrating factor value. If we rewrite this standard form of a linear differential equation, we'll say that it's y prime instead of dy dx, same thing, just different notation. And then we'll say plus py, we'll just drop the p of x to make it a little simpler. And then we'll say that this is equal to q. So same thing here, just a little bit simpler so it's easier for us to visualize what we're doing here. Remember here in step 4, we said that we would multiply through the equation by the integrating factor. Well, that's not a problem because algebra tells us that we can multiply through an equation by any value and we'll keep the equation's value the same. We'll keep the equation balanced. So we could multiply through this equation by anything that we wanted. We just happened to pick this function I of x. So let's go ahead and multiply through by I. So we'll say y prime multiplied by I. Then we'll say plus p multiplied by I multiplied by y equal to q multiplied by I. So we just multiplied through by this function I. Now, if we assume for a moment, we'll have to come back to this, but if we assume for a moment that we can replace this left-hand side with the derivative of I times y, so we'll rewrite this left-hand side as I times y, but then the derivative of that, leave the right-hand side the same. And again, we're just assuming this for right now, but we'll come back to it. So let's pretend that we can rewrite the left-hand side this way. If we do that, and then we go ahead and integrate both sides of the equation, which we can do. We can integrate two sides of an equation in the same way that we can multiply through an equation by some function we've chosen, I of x. Then once we've integrated, notice here on the left, we have the integral of a derivative. And remember, the integral and the derivative are operations that undo each other. So we get rid of those two things and we just have y on the left set equal to the integral still of qi on the right. Now we can solve this for y by dividing through by I, and we get y is equal to 1 divided by the function I multiplied by the integral of q times I. And this looks like a solution to the linear differential equation because we have an equation solved for y, and that's what we want for the solution to the equation. Notice also that based on what we found earlier, we said that the integrating factor I of x was equal to e to the 2x. That's what we found earlier for the integrating factor. Notice that if we plug all of the values that we know into this equation here for y, we will find the general solution that we found. So we get y is equal to 1 over the integrating factor, which we know is e to the 2x, so e to the 2x, multiplied by the integral of q, which is the function from the right-hand side, for e to the negative 2x, multiplied by I, so e to the 2x, and then dx. E to the negative 2x multiplied by e to the 2x. We add those exponents. The sum of the exponents is 0, so we get e to the 0, which is 1. So these two things cancel, and we're just left with the integral of 4. Remember that the integral of 4 is 4x plus c. So this entire value here becomes 4x plus c. And what we're left with is 4x plus c divided by e to the 2x, which was the solution that we found earlier. So this equation here that we built is actually a formula for the general solution to any first-order linear differential equation, which means we can either go through these steps to solve the equation, or we can use this formula directly. Of course, we still have to identify q, and we still have to find the integrating factor, but this is a formula that gives us the solution to the first-order linear differential equation. Now, that works, remember, as long as this step here is valid. Remember, we said we would circle back to this earlier. We just made this big assumption that we could rewrite this left-hand side as the derivative of I times y. In other words, for all of this to work, we have to show that it is okay to say I times y, the derivative of that, is equal to y prime I plus p I y. This left-hand side here of this equation is the derivative of a product. We have the product of I times y, and we're taking the derivative. So again, that should make us think of product rule. If we expand this left-hand side using product rule, we can say that the derivative of I times y is going to be equal to, first we'll take the derivative of y, so we'll say y prime, we'll leave the other function I alone, and then add to that the opposite situation. This time we'll take the derivative of I, and then we'll leave y alone. So using product rule, we know that this derivative of I times y is this expanded right-hand side here. What we're trying to show is that it's okay to say that this left-hand side is equal to this right-hand side. Well, when we compare these two equations, we can say that this first equation is okay as long as pi is equal to I prime, because everything else about these right-hand sides are the same. So this can be true as long as it's also true that I prime is equal to p times I. Now, if we rewrite I prime, the derivative of I, in Leibniz notation as di dx, and then we expand p and I as p of x times I of x, write them in function notation this way, then we can actually multiply both sides here by dx. So we say di is equal to p of x, I of x, dx. Then we can divide both sides by I of x. That will cancel I of x over here on the right, and we'll be left with 1 over I of x on the left. Then if we integrate both sides, which remember we said was always okay to do, we're doing the same thing to both sides of the equation, then over here on the left-hand side, we have the integral of 1 over some function. Well, remember from calculus that the integral of 1 over some function is the natural log of that function. So this left-hand side here, we can rewrite, we'll do it over here, we'll rewrite it as the natural log of the function I of x, and we now have that equal to the integral of p of x dx, Now, if we raise both sides to the base e, both sides of the equation to the base e, which we can do just like integrating both sides, we can raise both sides to the base e. It's the same operation, doesn't change the equation. We get the exponential and the logarithmic function to cancel with one another. Those are operations that undo each other. They're inverse operations. And so we're just left with I of x, the function on the left, equal to the exponential raised to the integral of p of x dx. And what we have all of a sudden is our integrating factor equation. And that's why this value works. That's how we get to this value for the integrating factor. It is the special value, this e to the integral of p of x dx. This is the special value that when multiplied through the whole linear first order differential equation will give us an equation that we can then use to find the general solution to that first order linear differential equation. Now, obviously going forward, to find the solution like we did here, this general solution y equals 4x plus c over e to the 2x, we don't need to prove the value of this integrating factor. We can just remember this formula e to the integral of p of x dx as the integrating factor value, and we can then quickly work through these steps in order to find the general solution. Or an even shorter version of this process, once we find the integrating factor, we can go straight to this formula for the solution to the linear differential equation, as long as we really understand what's going on behind the scenes. But those are the steps that we take to find the solution, y, the general solution, to the first order linear differential equation.